I welcome you all for this technical lecture on transmission line protection. There are a large number of transmission lines connecting different buses in a power system, and whenever a fault occurs on any transmission line, circuit breakers are to be opened at various places to prevent high current flowing in these transmission lines and in other parts of the power system. So for the protection of transmission line, the simplest way is to make use of overcurrent relays having IDMT characteristic. Now, overcurrent relay is good enough for protection of short lines directly connected to generators, but in a complex power system, all the transmission lines need not be connected directly to generators, and if the length of the line is long, then IDMT protection has to be provided on each bus separately, and that increases the operating time of the relay connected close to the source. Further, IDMT relays do not provide proper protection when we are using them on a line which is not directly connected to the generator, and also for different types of faults occurring on the system, a IDMT relay measures different current, and when current measured by a relay is different, in that case the proper discrimination of fault will not take place. Now, when the source to line impedance ratio is high, in that case a overcurrent relay becomes highly undesirable. If we take a source So this is a source directly connected to the bus, and here this is a circuit breaker used for opening the line. This is a current transformer to provide current to the overcurrent relay. Now, if there is a fault anywhere in the system, then depending upon the distance of the bus to the fault, a overcurrent will flow, and there is no problem in operation of the relay. In case there is an impedance present here, called source impedance ZS, then at different locations of the fault, the current measured by the relay will be different because of the voltage drop in the source impedance. Now, the source impedance comes due to the Thevenin equivalent circuit present before the bus, because say this bus is there and there is no direct generation connection, but there is a whole separate power system which has been represented by its Thevenin equivalent by a voltage source in series with the impedance. So, this is the Thevenin equivalent impedance of all the power system which is on the left hand side of the bus. In such a case, the current measured due to a fault here will be different as this Zs varies. Zs can vary because Zs is the Thevenin equivalent impedance of all the lines, transformer, generators connected on the left hand side of the buses, and due to change in configuration, it is possible that Zs may vary within wide limits. In such a case, the overcurrent relay will not able to discriminate the location of the fault exactly. Now, for the different types of faults, ये पूरा लिख के देता हूँ. So, for a single line to ground fault, the current IA is equal to 3 times voltage before fault EA of phase A, and divided by positive sequence impedance plus negative sequence impedance plus zero sequence impedance plus 3 times the fault impedance. Whereas, if the fault happens to be a line to line fault, so for a line to line fault, the value is root 3 EA divided by Z1 plus Z2 plus ZF. Z0, that is the zero sequence impedance, does not appear anywhere in the expression, and the value of fault current for the same location of fault, it is different. And for a double line to ground fault, and the current IA due to a fault at the same location. In the case of a double line to ground fault, it is different. Therefore, the relay cannot operate properly. And due to these reasons, it is not advisable to make use of overcurrent relays having identical characteristics only for simple cases where a radial line is directly connected to a generator. Now, for more complex cases where a transmission line is existing elsewhere in the system and we have to protect it, we make use of another type of relay which is known as distance relay. A distance relay obtains signal not only from the current flowing in the line, but also from the voltage of the bus. A typical arrangement So, a distance relay makes use of a current transformer. It obtains signal from the current transformer, and it also obtains signal from a potential transformer. And inside the relay, there is an impedance called replica impedance ZR, which is an equivalent impedance of the line. So, if the line is impedance is something, then if we multiply by proper PT and CT ratios, we can obtain an equivalent impedance which is connected inside the relay. Now, these current, voltages and the value of replica impedance are suitably processed to know the exact location of the fault point and whether the relay operates or not, the decision is taken accordingly. Say there is a fault here. On the line. Then the relay will find a ratio of the voltage inside the relay and current flowing inside the relay. So, it will measure the impedance between the bus and the fault point. In case the source impedance ZS varies, it will have no effect on the value of distance or value of impedance measured by the relay. So, measured impedance of the relay will be independent of the source impedance. Further, distance relays are made separately for line to line fault and separately for line to ground fault, because line to line fault, the impedance measured by distance relay is different, and for a line to ground fault or a double line to ground fault, the impedance measured are different. So, we see that how the impedance are measured by distance relays for different types of faults. On a three-phase system, we take the difference of voltage between phase B and phase C, divide it by difference of current of phase B and phase C. That is, we connect the secondaries of the potential transformer in star connection. So, by taking the voltage between two legs, we can take a voltage of VB minus VC, and we connect the secondaries of the three CTs in delta connection, so that IB minus IC is directly obtained from one of the corner of the delta connection. So, for So, for a double line to ground fault case, the impedance is VA by IA, and in denominator plus K times I residual is still more, because for a fault involving ground, the zero sequence impedance comes into play, and that is approximated by K into I residual. K depends upon the condition or the conductivity of the soil in the area, because earth current does flow through soil. Now, in these cases, we can clearly see that for a distance relay, all phase faults can be detected by similar relays, and all ground faults, whether it is a line to ground fault or it is a double line to ground fault, all the ground faults can be detected by another relay. So, in the actual system, for one relay represented here, there are actually 6 relays. Three for phase fault detection and 3 relays for ground fault detection. Then for backup purposes, we make use of a timer. That is, the relay located here can protect up to 80 to 90%. So, zone 1 is up to 80 to 90%. ZR is so selected that maximum line length which can be protected by this relay is up to 80 to 90% of this. We leave a little gap here, that is from 10 to 20% deliberately, so that any fault occurring on this bus may not be wrongly measured by this relay, and this fault occurring on this bus or here very close to the circuit breaker, that is sensed only by the relay located at this location and not by the relay at this location. Now, there is a time delay that is for the backup purpose. If due to a fault here, if this relay does not operate, then there is a timer inside the relay, and that timer changes the value of ZR. And due to changing the value of ZR, the relay at this location will able to measure fault up to zone 2. And zone 2 is plus 50%. Means this ZR will be reset by the timer such that the ZR is corresponding to 100% of the first line and plus 50% of the second line. So fault anywhere up to middle of this line will be detected by the same relay, but after a time delay. The time delay is, after some more time delay, ZR is further increased to cover up to this point. So up to this zone 2 and plus additional 10% to 20% of the third line after more time delay. So near fault, it operates quickly without any intentional time delay, and for the faults beyond it, it will give time for this relay to respond and protect. If this relay does not protect, then a backup will operate of this relay, which will trip here itself if the fault is anywhere from a starting point up to 50% of the second line. So this is a backup protection. In case the required relay does not operate, then after a further time delay, the relay will trip the circuit breaker itself after, if the fault is anywhere from this point up to 10 to 20% of the third line. So this is a backup protection provided for all the relays. Now the connection for backup protection. This is a fault detecting relay, that is a overcurrent relay, that shows that some fault has occurred somewhere. The relay should operate or should not operate will be decided by relay. So it is initialized. When this is closed, in that case, supply is available to the timer. Timer is having two contacts. First contact will close after T1 seconds when zone 2 fault is to be operated, and another contact which will close after T2 seconds. The Z1R is the replica impedance corresponding to the 80 to 90% of the line to be protected, and this is a signal going to circuit breaker. So if the fault is close to the relay, that is within 80 to 90%, of the length of the line. Then the fault detection relay will operate, and then this is the first zone. So if it is within first zone, this relay will also, this contact will also close, and supply will be available to the circuit breaker for tripping purpose. In case the fault is in the second zone, then first zone Z1R will not operate, but replica impedance will change, and it will be corresponding to first line plus 50% of the second line, and after elapse of time T1, this will close, and the supply will be available to the circuit breaker after T1 time delay, and this will trip the circuit. In case the fault is still far away, not detected by this and this settings, then in this setting it will be detected. So this will be closed after T2 seconds, and then the supply will be made available to circuit breaker. So the same 6 relays in which we are having a different values of replica impedances, we can use them for tripping in the first zone, or tripping in the second zone, or tripping in the third zone. Now the relays, how these are compared, how voltage and currents are compared. There are various techniques. Tripping signals. So we are taking both voltage signals and current signals and taking inside this. Now we want to see the process, how that these current and voltage signals are processed to go for a tripping or not. So if we see the processing of tripping signal, so we obtain two quantities. One is the operating other is the tripping signal. So we derive two quantities from the voltage and current signals received from PT and CT respectively. One is called the operating signals, means this signal will try to operate the relay to trip the circuit breaker. Other is restraining signal, which will prevent the relay from operation. So when the operating signal is more than restraining signal, the relay will operate. And when the operating signal is less than restraining signal, the relay will not operate. All the relays are working on the similar principle. Now, these comparison between the operation and restraining signal. The comparison is done by two types of comparators. One is called a amplitude comparator. Other is called a phase comparator. Amplitude comparator means if the amplitude of the operating signal is greater than the amplitude of the restraining signal, the relay will operate, and vice versa. Phase comparator will mean if the phase angle of the operating signal is greater than the phase angle of the restraining signal, the relay will operate. Now the signals of operating and restraining signals both can be either voltages or both can be currents. So again, there are two ways the operating and restraining signal can be voltage type or it can be current type. That is, the operating and restraining signal both can be voltages or operating and restraining signal both can be currents, but both must be of the same type. Then we can either compare their amplitudes or we can compare their phases. Now the ratio of operating signal to restraining signal is a impedance signal. An impedance signal should be so set that if impedance measured is less than a particular value, the relay should operate. If it's more than a particular value, the relay should not operate. So this can be graphically represented. That is, any method of comparing the operating signal and restraining signal we make use of, we can always represent it by this equation. T is the operating torque. So if T is greater than 0, the relay will operate. If T is less than 0, that is negative, the relay will not operate. Now here the relay voltage VR, relay current IR. Theta is the angle between voltage VR and the current IR, and tau is the angle of the replica impedance. That replica impedance consists of resistance and inductance. So what is the angle corresponding to that? That is represented by tau, and others are all constants. So this is the equation of any operating system whatsoever. We can take the real part of it and take imaginary part. That is, we separate this into real and imaginary parts, and we can graphically represent it on a RX diagram. So this is the R is the real part of the operating equation, and X is the imaginary part or reactive part of the operating equation. Now we can represent the transmission line where length of the line is equal to the impedance of zone 1, and whenever a fault occurs, the R and X will be lying on this line depending upon the location of the fault. Now, operating characteristic of the relay should be a snug fit to this line. Relay should unnecessarily not operate on this side, should not operate on this side, should not operate on this side, should operate only in the first zone. This is the characteristic of a circle. So, we can properly choose the values of K1, K2, K3, K4, etc. so that this makes a circle like this. This circle is a snug fit to this characteristic lies inside the circle, and if such a characteristic is used, the relay will operate if the fault point lies inside the circle anywhere, and it will not operate if the fault point lies outside the circle. This characteristic is known as Moe characteristic or Moe relay. Now, this is all right a characteristic, but the fault will have generally a fault resistance, and as the fault resistance will be like this, this will be the arc resistance. But still, a lot of tripping area is there which is not within the fault zone. This is the fault zone. Fault point will lie somewhere in this zone only. It will not lie here, it will not lie other places. So, if the fault or if the operating point somewhere lies outside the fault area, so this is the fault area. There, if it lies outside the fault area, but lies inside the circle, relay will still operate. That means, even if there is no fault, still the relay will operate. Now, whenever the fault is there elsewhere and that fault is cleared, the machines will swing. VR and IR both will be changing in the system such that the operating point will swing. So, if the operating point swings like this and it passes through the circular characteristic of the relay will operate even if there is no fault. And this is a disadvantage of a Moe relay, that it is likely to operate under swing conditions when the fault is somewhere else and it is cleared also by the circuit. Now, to avoid this, we make other characteristics. That is, the Z or the replica impedance is selected as a pure inductive reactance of the line. In such a case, we can obtain a characteristic which is straight line, and if the fault occurs such that reactance of the line between the bus and the fault point is less than what is given here. So here, this zone, anywhere the reactance is falling, the relay will operate, and if the reactance is more, then the relay will not operate. This relay will not be sensitive towards fault resistance. The fault is mostly due to arc, and inductance of the arc is negligibly small. Prominently, the arc is consisting of resistance only. So any value of arc resistance will not affect the relay, and relay will still measure it correctly. Now further, to have a snug fit to the fault area, we can have two circles intersecting each other by making use of two relays, and so this is called a lens type characteristic. It is also possible to have four lines covering this area, and this is called when only electromagnetic relays were available. Moore type characteristic was most popular, but nowadays static relays, numerical relays, or even microprocessor based relays have become very popular, and it is very easy to construct a quadrilateral characteristic or a lens type characteristic which is having a minimum area or minimum extra area outside the fault zone, and these relays are often used. So this way we see that a distance relay is superior compared to a overcurrent relay, and these are extensively used in all the power stations and substations for protection of various lines. Thank you.